Hello everyone and welcome to this video. This is Fluid Mechanics Assignment 1 and we are Group 4. In this video we shall demonstrate and explain the following concepts: viscosity, buoyancy, continuity and Bernoulli's principles, and lastly momentum theorem.
Today, I'm going to explain what is viscosity and its application in our daily life. Firstly, viscosity is the resistance of the fluid to deform at a given rate. It also describes the fluid's resistance to flow. There are two types of viscosity, which are dynamic viscosity and kinematic viscosity. Kinematic viscosity is the measure of the fluid's internal resistance to flow under an external force, while the dynamic viscosity under the gravitational force only. For your information, viscosity is an extensive property that will not be affected by this amount. On the other hand, it can only be affected by the temperature and pressure. When the temperature increases, the viscosity of the liquid decreases and the viscosity of the gas increases. When the pressure increases, the viscosity of the liquid increases and the viscosity of the gas decreases. Now let's talk about the application of viscosity in our daily life. You might be wondering why honey flows slower than water. It's because the viscosity of honey is higher than water. When honey is stored in the refrigerator, it can hardly flow due to its high viscosity. But when it is stored at room temperature, it will flow faster due to the increasing temperature that decreases the intermolecular forces between the molecules, and therefore the viscosity of the honey drops. When the honey is heated further, it will be at its highest flow rate with the lowest viscosity. Another application of viscosity is shown in the usage of brake oil in vehicles. Brake oil works as a hydraulic fluid in the hydraulic brake or clutch. It plays a vital role in transferring the hydraulic pressure from the brake lines to the brake caliper. Therefore, the brake fluid must be able to flow easily through the brake lines to the piston. Thus, it's important to use a low viscosity brake oil in the vehicle so that the oil can withstand a high range of temperature to support the system of the car. Now, let me show you the demonstration of viscosity in real life. Here, I will take the example of honey that we discussed earlier. It is shown that at the same temperature, honey flows slower compared to water. This is because honey has a higher viscosity than water. When the honey is just taken out from the refrigerator, it flows very slowly due to its high viscosity caused by low temperature. When it stays under room temperature, it flows faster compared to just now because the increasing temperature decreases the viscosity. Last but not least, when the honey is heated, we can find that it flows at the highest speed due to the lowest viscosity. That's all for my part. Let's move on to the buoyancy part.
Buoyancy refers to the upward force exerted by a fluid on an object when it is submerged in that fluid. It represents the ability or tendency of an object to float in water, air, or any other fluids. When an object remains still and is fully or partially submerged in a fluid, the resulting force from the fluid is known as the buoyant force. According to Archimedes' principle, when an object is immersed in a fluid, the upthrust is equivalent to the weight of the fluid it displaces. Archimedes' principle shows that a change in the mass of the object affects the amount of the liquid that has to be displaced. In submarines, this is controlled by the ballast tanks. Unlike the ships, submarines have the ability to control their buoyancy, allowing them to submerge or resurface as desired. To control its buoyancy, submarines are equipped with ballast tanks that can be filled with water or empty using the compressed air. When the submarine is floating on the surface, the ballast tanks are filled with air, resulting in the submarine having a lower overall density compared to the surrounding water. If the submarine is submerged, the upthrust remains unchanged but the weight of the submarine increases due to the water inflow, causing it to sink more rapidly. During the descent of the submarine, water is allowed to enter the ballast tank while the air is released, resulting in an increase in overall density of the submarine. This process continues until the submarine becomes denser than the surrounding water, causing it to attain negative buoyancy and begin to sink. order to maintain a steady position at a specific depth, the submarine maintains at an equilibrium between air and the water in its ballast tanks. This balance is important to achieve a state of neutral buoyancy, where the submarine's overall density equals to that of the surrounding water. When the submarine rises to the surface, the compressed air is introduced into the ballast tanks. The water is forced out of the submarine, and this continues until the overall density of the submarine becomes lower than that of the surrounding water, resulting in positive buoyancy. The video below demonstrates how the ballast tank works.
Fluid dynamics is the study of how fluid behave in motion. Two fundamental principles that describe this behavior are continuity and Bernoulli's principles. Continuity is a fundamental principle of fluid dynamics that states that the mass of a fluid must remain constant as it flows through a pipe or a channel. This means that the mass of a fluid entering a section of a pipe is equal to the mass of fluid exiting that section at any given point in time. For incompressible fluid, the density is constant. Therefore, mathematically, it can be expressed using the following equation, where A is the cross-section area and V is the velocity of the fluid. In the case of compressible fluid, the density changes along the flow. Thus, it is expressed in terms of mass conservation as followed. To illustrate this concept, imagine a garden hose with water flowing through it, as it's shown in the right hand of the screen. If you were to replace it with a hose that has lower cross-section area, as the case in the lower video, you would notice that the water would shoot further and faster. This is to ensure the continuity of mass flow. The continuity principle states that a decrease in the cross-section area will respond to an increase in fluid motion, and the following experiment will prove this statement. An empty bucket was filled with water to obtain the volumetric flow rate. It took 38 seconds to fill the empty bucket with 3 gallons of water. Mathematically, the volumetric flow rate was obtained by dividing the volume over the time, as followed. And by using the continuity equation, fluid's velocity can be obtained by dividing the flow rate over the area, where the area was obtained using the diameter of the hose, which is 1.5 centimeter. Therefore, the fluid's velocity at the green hose is approximately 1.69 meters per second. By knowing that the water flow rate is constant and by carrying the previously obtained results, the continuity equation can be used to calculate the fluid's velocity in any other pipe. Shown in the video, a blue hose has a lower diameter of 0.8 cm, and by performing some calculation, as shown in the bottom right of the screen, the velocity of the blue hose was approximately 5.95 meters per second. Therefore, we can conclude that a reduction in the cross-section area will follow with an increase in the fluid's motion. Bernoulli's principle, named after the Swiss mathematician Daniel Principle, is another fundamental principle of fluid dynamics that relates the pressure, velocity, and elevation of a fluid in a streamline. It states that within a streamline of a steady flow of an incompressible and non-viscous fluid, the total mechanical energy per unit mass of the fluid remains constant. Bernoulli's equations come in different forms. Head form and energy form are used for internal flows. Pressure form is normally used for external flows. However, when using Bernoulli's equation, several assumptions are made to make it applicable. These assumptions include ideal fluid, steady flow, incompressible fluid, one-dimensional flow, and constant energy. Bernoulli's principle states that as the velocity of a fluid increases, the pressure within the fluid decreases, and the following video will illustrate this statement. Consider a piece of paper like the one I'm holding in the video. I'm going to place it beneath my lips and blow. Notice that the paper goes up. This is due to the pressure difference. The fast-moving air on the top of the paper results in lower pressure. Therefore, the high pressure beneath the paper pushes it up, generating lift. This is quite similar to how an airplane wing generates lift. As air flows over the curved surface of the wing, its velocity increases, causing the pressure above the wing to decrease, and as a consequence, the pressure force beneath the airplane pushes it up, creating lift. Therefore, Bernoulli's principle is widely used in practical applications, including the design of aircraft wings. To prove and illustrate Bernoulli's theorem, the following experiment was performed using 2 straws and a jar filled with water. And by placing the longer straw in the water and the shorter straw above it, as it's shown in the video, notice that by blowing through the shorter straw, the air rushes out with great speed and goes over the other straw with even greater speed. This leads to lower pressure over the straw in the water, so the water rises and hits the great moving air above it. The creation of low pressure due to high-speed air is according to Bernoulli's principle, which again states that an increase in fluid's velocity results in pressure reduction.
The momentum equation expresses Newton's second law by relating the sum of the force acting on a fluid element to its acceleration of rate of change of momentum. In open channel flow problem, the momentum equation is used to calculate unknown force acting on the wall or bed of a control volume. The momentum equation can be written using Newton's second law of motion, which equates the rate of change of momentum m equals mv with the algebraic sum of all external force. Below are the equations of it. The application of momentum equation. The momentum equation is used to calculate the force exerted on the boundary of a flow passage by a stream of flowing fluid as the flow change direction, magnitude, or both. The momentum equation is used in the following practical applications such as flow through bendpipe, jet propulsion and propellers, fluids flow through stationary and moving plate or vane. Non-uniform flow through sadden a large pipe. And the last one is hydraulic jump in open channel. These are the experimental of momentum equation. As the balloon inflates, for the explanation of the balloon inflate, the application of conservation of momentum. When you release an inflated but untied balloon that has been placed at rest, the gas inside will quickly escape from the open end. This is due to the momentum conservation principle. The expelled gas causes the balloon to recoil. In this case, the released gas and the balloon form a closed system, and the system momentum is conserved. The balloon flies across the room because the momentum of the balloon and the momentum of the remaining gas in the balloon are equal in magnitude, but opposite in direction to the momentum of the released gas.
To apply the momentum theorem, assume that it's at room temperature and an atmospheric pressure of 1 atm. With the following assumption, we can calculate the momentum of the escaping air. Mathematically, the volumetric flow rate was obtained by dividing the volume by the time, as followed. By using the continuity equation, air velocity can be obtained by dividing the volume flow rate over the area. Therefore, the air escaping from the hole has a velocity of 4.069 meters per second. By multiplying the rho by the volume of the balloon, the mass of the air was obtained as followed. With the above results, we can now calculate the momentum of the escaping air, which is found to be 0.0367 kg by meter per second. As the balloon acquires momentum which is exactly opposite to the momentum of the escaping air, we can conclude that the momentum of the balloon is 0.0357 kg by meter per second. That's all that we have in this video. Thank you for your time and have a great day.